Well, in this fourth presentation in the Introduction to VHDL playlist, we will address regular sequential circuits. And this corresponds to chapter 4 of our book. The expected learning outcomes that you will achieve are you shall be able to differentiate between regular sequential circuits, finite state machines, and finite state machines with data path. You shall also be able to write a VHDL description for basic building blocks and for regular sequential circuits themselves. Well, to start with, regular sequential circuits have this property of exhibiting a simple and repetitive pattern. Counters and shift registers are examples of regular sequential circuits, and in the case of counters, be it up or down counters, they will simply increment or decrement, so the state transition is indeed a simple and repetitive pattern. And likewise, shift registers, they will either shift right or left, and again we have a very simple state transition pattern. Now, on the contrary, when we come into situations like a sequence detector or, for example, a parity generator, then we are considering also examples of sequential circuits, but where the state transition pattern is not as regular as in the cases that we have seen before. So in these cases, the state transition patterns are tailored to meet the specification requirements, and they will be irregular in most cases. And in this case, we are talking of what we call finite state machines. Finally, we have also larger, more complex circuits that are known as finite state machines with data path. And in these cases, a finite state machine will be used as the controller of other regular sequential circuits like counters or shift registers, which comprise what is called the data path. Well, a microprocessor architecture might be seen as an example of a finite state machine with data path, and in this case the controller finite state machine is the instruction register and the instruction decode and control unit, and the data path comprises the program counter, the data registers, the arithmetic and logic unit, for example, and all these blocks are controlled by the instruction decode and execution control unit, which is the finite state machine playing the role of the architecture controller. So finite state machines with data path are a larger and more complex form of sequential circuits, and we will be using it during our course as well. Well, we will start by looking into the VHDL description of a basic D-type flip-flop with an asynchronous reset, which has the truth table shown in the right of this slide. What this truth table tells us is that the output of the flip-flop will retain its value, except when the case of the reset input is asserted to 1, in which case the output goes to 0 immediately, or when there is a rising edge in the clock signal, in which case the output takes the value of the input. So when we have a rising edge in the clock, the input D is copied into the output Q. So if we build a VHDL description for this circuit, the entity declaration will simply list the inputs and outputs, which in this case are all of the standard logic data type. And then the architecture body will tell us that we need to have a process comprising these two signals in its sensitivity list, because either when there is a rising edge in the clock or when reset goes high, the process has to execute. And what the process does is that it checks if the reset input is 1, in which case Q will take the value of 0. Else, if there has been an event in the clock and the clock signal is actually 1, which corresponds to a rising edge, then Q takes the value of D. That is to say, the output takes the value of the input. And if and process and architecture. So this is the VHDL description for a D-type flip-flop with asynchronous reset. Now this same structure can also be represented using what is called a two-segment coding style. Now this is a very important coding style that we will use repeatedly through our course, and which is also used many times throughout the book. So it is important that we understand what this represents. The two-segment coding style actually assumes that we are looking into architecture sequential circuits that can be represented as shown here, and this represents a block diagram of a synchronous system. Well, synchronous systems will have what is called a state register, shown here in the middle. This state register comprises several flip-flops, not just one, as you might be led to think from this representation. The state register comprises several flip-flops, and their outputs represent the current state, which we will refer to as state underscore reg. And of course their inputs, which will be copied to the output when there is a rising edge in the clock, then their inputs represent the next state of the sequential circuit. So they are called state underscore next. Well, the next state is generated by the combinational block called next state logic, and this block takes as inputs the current state coming from the outputs of the flip-flops and the external inputs coming from the external world. So the next state of the circuit will be a function of its current state and of the external inputs. While the circuit will also produce a set of outputs to the external world, and they will be a function of the current state, and they may also be a function of the external inputs. And so when we build a VHDL representation for a synchronous system, we'll always have these three blocks: the state register, the next state logic, and the output logic. Now if we apply this model to the simple D-type flip-flop with asynchronous reset, and in this case we have added an enable signal. Now what we see here is that if enable is at 1, then this multiplexer is connected to the upper input, meaning that at the next rising edge of the clock, the input will be copied to the output. On the contrary, if enable is at 0, then the multiplexer will be connected to the lower input, meaning that the next state will correspond to the current state. Now the way to code this in VHDL is again through a process, but in this case we will be using this two-segment coding style, and two-segment means that we will define the current value, which is defined as underscore reg, and the next value, which is defined as underscore next. These are the two segments used in this coding style. Well, in this case these are signals of the standard logic type, and I should call your attention to the fact that the book uses the Q underscore reg and Q underscore next names in the diagram, but then in the VHDL listing they are referred as R instead of Q. Apart from that, you shouldn't have any problem to understand this description. So what we are saying here is that this process depends on clock and reset. Again, if there's a transition in the clock or a transition in reset, then this process will execute. And upon execution, what it will do is that if the reset is at 1, then the current state takes the value of 0. Else, if there has been a rising edge in the clock, then the current state takes the value of the next state. And this is a very universal representation of the state register, which we will see that is used exactly like this, be it for a counter, a shift register, or any higher register transfer level, rather than just a flip-flop. Now the next state logic, in this case this block corresponds to the multiplexer and the simple flip-flop that we are considering. So in this case the next state logic is described as R next takes the value of D when enable is at 1, else it will take the current value. So actually this is a concurrent statement which is of the conditional signal statement, signal assignment type, and it corresponds to the next state logic block. Now in this case the output logic is simply a direct connection, so what we say is that the output logic simply consists of specifying that output Q takes the value of R underscore reg, so the current state goes to the output directly. Well, we could actually move up from 1 bit to 8 bits or to any number of bits, so this would be moving to register transfer level. The VHDL description will be very much the same. Essentially the difference is that when defining the entity, we will no longer be using standard logic alone. In this case it's a standard logic vector data type, since we'll have a bit array both for the input and the output. And then in the state register process, which in this case was a single flip-flop, so we would reset it by allocating it the value 0. In this case it's a bit stream that has to take the value of 0, so we have this construct available in the VHDL, which means any number of bits that are comprised in this variable key will be set, Q will be set to 0 by specifying it in this way. They could of course be set to 1 if we set others 1. Apart from that, the rest is the same. When there is a rising edge in the clock, then Q takes the value of D. This is the difference in imposing the reset operation, which you should be aware of. Now, I won't go in detail into this example. I'll leave it to you to check on pages 78 and 79. But the interesting thing in defining a register file, which is simply a set of registers, is that there is no predefined data type to represent this structure. So we will have to create what is called a user-defined data type. And we can do so inside the architecture body by using the keyword type, and then we will name our new data type. In this case we will call it register file type, and we will say that it is an array with these many elements of standard logic vector type. So we have just defined a new user-defined data type, which we have called register file type, and since we have defined it, we can now use it by creating or declaring a signal called array register, which is of the register file type that has just been created and which will correspond to this structure. You may check this example on pages 78 and 79, as I said, but it is the important thing to refer in this case is that it introduces the creation of user-defined data types, which we will use whenever we design finite state machines. Now, to conclude, we will look into three regular sequential circuits. These are the universal shift register, the universal binary counter, and the modulus M counter. Now, first interesting thing to call your attention to is that the register block and the register state block is the one that is located in this position here. It is always the same whatever type of regular sequential circuits we are considering, and that is because what the register state does is always this. It will take the value all zeros when reset is at 1, or else if there's a rising edge in the clock, then it will take the next value. And this is the same whether this is a counter or a shift register or whatever. So the state register is always represented like this. Actually, if we go from the shift register block into the binary counter, you will see that it is the same. If reset is equal to 1, then the current state takes the value of all zeros. Else, if there is a rising edge in the clock, then the current state takes the value of the next state. The same happens for a modulus M counter. Now, the difference, as I said, is that the next state logic is defined differently. So if we look into the universal shift register case, the next state logic, and now notice that this block is describing what is inside this combinational box. The next state logic, as I said, will be defined using a concurrent signal assignment, and in this case it's the selected signal assignment that we are using. And what we are saying is that in this case we have two control bits, and their role is as described here. So if they are both at 0, this means that no operation is to take place. If they are 0, 1, that it will be shift left. 1, 0 is for shift right, and 1, 1 will represent parallel load. So in this case our shift register will have n parallel inputs and n parallel outputs, and we can load the inputs to the outputs directly and then start shifting left or right. So the way we define the next state logic, as indicated here, is that the next state will take the value of the current state when both control inputs are at 0. If that is not the case, then if they take the value of 0, 1, meaning that we will shift left. Shifting left means that we will discard the most significant bit, which was n minus 1. So starting from n minus 2 down to 0, they will take the leftmost positions, and in the least significant position we will now insert the least significant parallel input. So what was before bit n minus 2 is now taking the position of n minus 1, that is to say the most significant position. And we have done so by concatenating those bits that were to the right with the least significant input. Now when we want to shift right, what this means is that the bit taking the rightmost position will be discarded when it is shifted out. So all bits will shift left one position, meaning that the bit that will now be in position 0 is the one that was previously in position 1. They will all have shifted one position to the right, and the leftmost bit will be taken by the most significant bit of the parallel input. So we will shift right by concatenating the bits that were all on the left with the leftmost bit of the parallel input. And if we want to load value of the parallel inputs. I strongly recommend that you go to pages 80 and 81 of the book, see what listing corresponds to the universal shift register, and then just open this example in the Xilinx design tool in the project navigator and create a simulation, so create a test bench for this circuit and see the waveforms that result from simulating this code. Now, if we go from a universal shift register into a universal binary counter, there is little else to say. The state register is the same, and essentially there are two things that I would like to call your attention to. In this case, they are that this counter, besides being able to count up and down, it is also able to do what is called a synchronous clear operation. And this means that we have two ways of resetting the outputs. One is the asynchronous reset signal that we are already familiar with, but now we have what is the synchronous clear signal. And when the synchronous clear input is at 1, then the next state will take the value of all zeros. But now the next state will only become the current state when there is a rising edge in the clock. So this synchronous clear is indeed synchronous in the sense that our next will become all zeros, but this will become the current state only when we have the next rising edge in the clock. Now, the second interesting thing to call your attention to is that we have a load input as well. And if load is at 1, then the next value will be the parallel inputs of this counter. However, the parallel inputs called D, these are the inputs to the counter, and so they will have been defined as standard logic vector data type. And now because we as a counter want to add or subtract 1, our next and our reg, they have to be defined as unsigned data types. And so we have the interesting example here that we need to carry out type conversion. If we want to allocate the inputs to the our next signal, then we have to convert from standard logic into unsigned. And likewise, when we want in the output logic block to allocate to the outputs Q the current values of our underscore reg, we have to convert from unsigned into standard logic vector data type. So notice that this universal binary counter has a synchronous clear input, and it also uses typecasting or type conversion to match the data types of the R next and R reg and the Q and the pins. Again, I would recommend that you go to pages 82 and 83 and see what listing corresponds to this example, then create a project in the project navigator, create a test bench and see the binary counter in operation. This is actually the best thing that you can do to learn, because seeing it in practice will help you to understand how these structures work. Finally, the modulus n-m counter is simply a counter that instead of going through the full range, it will restart at 0 whenever it has gone through m states. So say it might be a 4-bit counter. With 4 bits we might count from 0 to 15, but we might just be interested in counting from 0 to 10. And in this case that would be a modulus 11 counter, because from 0 to 10 we have 11 states. And so what we would say is that, again, the state register description is the same as for all the other blocks, but the next state logic will be defined as r underscore next takes the value of all zeros when we have reached the limit count state, or else it will add 1 to increment. Adding 1 again means that this is the unsigned data type, so when we in the output logic allocate the values of our regs into output queue, we will have to convert them from unsigned to standard logic vector data type. This example is presented in pages 83 and 84, and again I strongly suggest that you take the time to copy or to open this listing file in the project navigator and carry out this example in test bench.